Hello and welcome back for lesson 9.4. We are now going to be working with data that is testing two means, so still quantitative data, except for they're matched or paired samples. So when we did our intro questions in lesson 9.1, we looked at this question right here, where a researcher was collecting the heartbeats per minute on coffee drinkers before they drank coffee and also 15 minutes after they drank coffee. So this is going to be a paired data. There's going to be before and after. And so we're still going to have similar requirements. Simple random sampling. Our sample sizes are often small in these samples. There's going to be two measurements on pairs of individuals or objects. We're going to calculate the differences on the matched pairs, and then the differences are going to be sampled as a single difference. And then because it's a t-test, we are going to have a degrees of freedom of n-1, and then this is going to be our test statistic. And we're going to be following, this is in your formula packet for matched pairs under 9.4. And this is the Desmos program that we're going to be using. We're going to be using a one sample because after we take the differences, we're going to be calculating a hypothesis test for just one sample then. So here are the 4 requirements which we've been using. And this is our 6 steps, which should look very similar, except for now in our hypothesis statement, we're just testing to see if our differences are either equal to 0, if our differences are negative, meaning our befores are less than our afters, or our differences are greater than 0, where befores are greater than our afters. And so our test statistic here is, this is D bar, it's hard to read there. But let's just jump right in. Here. So a study was conducted to investigate the effectiveness of hypnotism in reducing pain. Results from randomly selected subjects are shown in the table. A lower score indicates less pain. The before value is matched to an after value, and the differences are calculated. So this is subject A, and their before value was 6.6, and then it actually went up to a higher pain at 6.8. But then subject B, their before pain was 6.5, and it went down to 2.4. So then we're going to calculate the differences. We did that here in the table. Here's the, we took the after data and we subtracted the before data. So we took the after and subtracted the before. Because we would think that the after would be less than the before, is what we hope, right? We hope that their pain goes down. So we hope that this is a negative value. Okay. So when we took the differences, the after minus the before, we are, the first one, remember their pain went up, so they have a positive difference. But here's the differences. And now we're going to find the sample mean of the differences. So the sample mean of the differences is labeled down here. It's a negative 3.13. And then the sample, the standard deviation of the differences is 2.91. And we can use that in our, to calculate our test statistic here. It's the X bar of the differences, subtracting 0. So it's really just the X bar of the differences. And then the standard deviation of the differences divided by the square root of n. So remember that this is the, let's write it so you can read it. X bar of the differences. X bar of the differences is what goes here. Okay, and then we have our test statistic is negative 3.04. And so we are going to find our critical T. So our critical T value is the T of our degrees of freedom, which is 7. N minus 1 is 7. And 0.05. And we're thinking that our differences are going to be less than 0. So it's going to be a left-hand test. So it's going to be over here. So our critical T value is a negative 1.89. This is our danger zone over here if we use the classical approach. And our test statistic is negative 3.04. So we did fall in the danger zone. In the danger zone. So that's why we reject H0. And we can go to the program and show that our 0.05 is our p-value is 0.0095, which is less than our alpha. And I'm going to show you. That we can put in our sample here of 8. And the sample mean we said was a negative 3.13. And we think the difference should be 0 down here, the M0. And the sample standard deviation of the differences was 2.91. And then we can go down and click on the less than. So I'm clicking on the less than test. And then there's our p-value. And I'm just validating here is our test statistic. So our p-value is 0.0094. And the one I have on your notes is 0.0095. And that's just because of some rounding when I did my hand calculation. So my p-value is 0.0095, which is less than 0.05. So this is the p-value approach. This is using the classical approach, but either way, we reject H0. So at a 5% level of significance, there is sufficient evidence to conclude that the sensory measurements on average are lower after hypnotism. Hypnotism appears to be effective in reducing pain. So let's look at our first example. I encourage you to have the Desmos file open, where I have all of the data for this lesson, and you can see where I calculate everything. So example 2 says a study was conducted to investigate how effective a new diet was in lowering cholesterol. Results for the randomly selected subjects are shown in the table. The differences have a normal distribution. And they're asking, are the subject's cholesterol levels lower on average after the diet? Okay, so we would think that they should be lower. So I'm going to take my befores minus my afters. Actually, yeah, I'm going to take my befores minus my after. See what we did here in the program. So here is the file and the cholesterol, and I did the befores minus the after. So I put my befores in X1, my afters in Y1, and then I just took the differences. And then I can tell Desmos to take the average of those differences of X1 minus Y1 and the standard deviation of those differences of X1 minus Y1. And then I can take my mean and put that in for my test statistic. And again, we can use the computer program, but I wanted to show you how I got my test statistic here on my own. So I will show you my paper momentarily, but my test statistic is 2.7268, and our critical T value for the danger zone is 1.8595. And so going back to our paper here, on the statement where our mean zero is that the mean of the differences is equal to zero, and we're testing that the mean of the differences is greater than zero because we think that the befores are bigger than the afters. Okay. And then we would just subtract these, and you can see those differences in Desmos. And so there's our test statistic. Here's our critical T value. And so 1.8595. And this is the danger zone. And our test statistic is definitely in the danger zone. The T0. So our test statistic is greater than the critical T. .7268 is greater than 1.8595. And so I'm going to go back to my program. So I'm going to just show you here that we can go ahead and just put in our samples. That we have 1, 2, sample size was 9, and it was a negative 3.13, I believe. Nope, our average, the mean we had was 10.78. This is 11.86 over here, and then we're testing against 0, and then that validates our T0, 2.2768, and then we're testing a greater than this time, and so there's our p-value, and the p-value is 0.01299, and the alpha is 0.05. And you can see that our p-value is less than our alpha, and we are in the danger zone. So both ways we do reject H0. So in our conclusion, we're going to state there is sufficient evidence to say that the new diet lowers cholesterol. Let's check out example 3. Example 3 says a college football coach was interested in whether the college's strength development class increases players' maximum lift in pounds on the bench press exercise. He asked 4 of his players to participate in a study. The amount of weight they could each lift was recorded before they took the strength development class. After completing a class, the amount of weight they could each lift was again measured. The data was as follows. So we're hoping that it goes up. So we are hoping that the weight that they can lift is more. And so we're going to do after minus before. So 295 minus 205 would be 90, and then 11, and then a negative 8, and then a -8. So they lifted less, and each of them lifted more. And then we're going to average those values here. Okay. So the coach wants to know if the strength development class makes this player stronger on average. So we're going to average the differences. And the average that you can see is in my Desmos program is 21.3. 21.3 minus 0 over, and then the standard deviation of the differences is 46.7. Down here in our test statistic, or this is our T0, is 46.7 divided by the square root of 4. And that comes out to be 0.9122. So we're testing a single mean, basically. And so our H0 is that the mean differences are equal to 0, and our HA is our mean differences are greater than 0. And that's what we're testing. And so we have a right tail test of the picture. And our critical T-value of degrees of freedom is 3 and 0.05 is 2.353. And so 2.353 is our danger zone, but our test statistic is here. Our actual data is here, so we're not in the danger zone. And if we put it in the program, our p-value is 0.2144, which is greater than alpha at 0.05. So both of these always will be in agreement, the classical and the p-value approach. So we do not reject H0. So in our conclusion, there is not sufficient evidence to support the claim that the strength class increased maximum weight lifted. So unfortunately, there's not enough evidence to support that the class is helping increase how much weight they can lift. Okay, so catch me back. I'm going to make a video for the last 3 questions in this lesson, 4, 5, and 6. If you want to watch them, they're not required. But if you need some more support in this, I'm going to make a second video to lesson 9.4.